Hi everyone, this is a pre-lab lecture video on the Williamson ether synthesis. Okay, so we're doing an organic synthesis, which is common type of experimental reaction for second semester organic chemistry. The reaction we're doing is the Williamson ether synthesis. The overall reaction starts with either an alcohol or a phenol, and that's represented by the ROH. It utilizes a base, so in this case, sodium hydride is being shown over the arrow as the base, followed by introduction of an alkyl halide in order to form an ether, which we see as the product. You can form symmetrical or unsymmetrical ethers this way. It would be symmetrical if the blue R and the red R are the same group, and unsymmetrical if they're different groups. Once the alcohol is deprotonated by the base, it forms what you might call an alkoxide if you use a regular aliphatic alcohol, or if you had started with a phenol or a phenol derivative, you would call it a phenoxide. Either way, it's a strong nucleophile possessing an oxygen with a negative charge, which is great for an SN2 reaction with an unhindered alkyl halide, which is drawn here as Rx. The reaction goes through an SN2 mechanism between the alkoxide or the phenoxide and the alkyl halide. What do we use to consider to choose the base in the reaction? Well, part of that depends on the starting material, whether or not you use a phenol or an alcohol. Phenols are the common name for an aromatic alcohol, which is basically a phenyl ring or an aromatic ring directly attached to an OH group. Phenols are more acidic than aliphatic alcohols, with a pKa of around 10 compared to alcohols, which generally have a pKa of around 16 to 18. Because the phenol is more acidic, we can get away with using a weaker base. On the top here, we have a reaction with hydroxide. Hydroxide can act as a base and deprotonate the phenol, forming phenoxide and water. If we analyze the pKa value of the acid and the conjugate acid, we see that the conjugate acid, water, has the higher pKa value. So we know the equilibrium will favor the formation of the products in this reaction. And more specifically, there will be 10 to the 6 more products than reactants at equilibrium. If we compare that to using an alcohol, such as ethanol, as the starting reactant, and deprotonating that with the same base, hydroxide, what we see is that the acid and the conjugate acid have about the same pKa value. This means that the concentration of reactants and products will be about 1-to-1 in the reaction mixture. That's not ideal because then you'll have 2 strong nucleophiles in solution. You'd have hydroxide and ethoxide, both of which could potentially do an SN2 reaction with whatever alkyl halide you add into the reaction mixture next. So if you were using an alcohol starting material, you would probably want to choose a much stronger base, such as, for example, sodium hydride. Sodium hydride is not only a stronger base, but also it's considered a non-nucleophilic base. So it can shut down any potential side reaction of the base acting as a nucleophile in the reaction. So sodium hydride, we can see on the bottom here, would also deprotonate the aliphatic alcohol, forming an alkoxide. And in this case now, the pKa of the acid is 16 and the conjugate acid is 36. So this is not much of an equilibrium at all. The reaction will essentially go to completion, and in addition, if we allow the hydrogen gas to bubble out of solution, that will form a driving force to form more products. So sodium hydride is a great choice for base if you were using an aliphatic alcohol. However, we're using in our experiment a phenol derivative. So we're going to use the weaker base, the hydroxide base, instead of sodium hydride. There are some advantages to this as well. Sodium hydroxide is obviously much cheaper and more readily available. Sodium hydride is more reactive as a base, so it's more difficult to handle. You have to be careful to not expose it to too much water, which can come from the atmosphere, and that can decompose the product. So it's not as easy a reagent to work with. So that's one advantage in being able to use hydroxide. The second part of the reaction involves an SN2 reaction of your phenoxide, or in the case of a different reaction, an alkoxide, with an alkyl halide. The first thing that should be said about the alkyl halide is the carbon attached to the leaving group, in this case called the alpha carbon, has to be sp3 hybridized. So for example, where you see this methyl group, that could not be a phenyl group because the carbon attached then would be sp2. And remember, we cannot do SN2 or SN1 reactions on an sp2 hybridized carbon. So the alpha carbon must be sp3 hybridized, and it is in all of the cases shown here, a methyl primary, secondary, and tertiary alkyl halide. However, it should be noted that for the Williamson ether synthesis, because we're relying on an SN2 reaction, it's most preferable to use a methyl or a primary alkyl halide. That will produce the highest yield of product. As you move to potentially a secondary alkyl halide, you're going to increase the amount of elimination product, and will actually outcompete substitution, and elimination will be the major pathway, E2 to be more specific. So that means you're going to get a low yield of the SN2 product, which is the desired ether product. As you move to a tertiary alkyl halide, the reaction will not progress at all in terms of an SN2 reaction to produce the desired product. Instead, exclusively you'll get E2, and you will not produce any of the desired product at all, and get essentially no yield. So to summarize, it's much better to have an unhindered, preferably methyl or primary alkyl halide in the Williamson ether synthesis. There is a potential side reaction in the reaction experiment, which is what happens if you're adding hydroxide to the reaction mixture. What happens if it doesn't completely deprotonate the phenol, and there's some still around, and it could potentially do an SN2 reaction and act as the nucleophile and kick out bromide to form benzyl alcohol. That is certainly possible, particularly if you have an excess of sodium hydroxide around compared to the phenol. It's not so much of a problem if you have a 1-to-1 mole ratio of the phenol and sodium hydroxide, because deprotonations are fast. So as soon as the sodium hydroxide is added, it's much faster for it to deprotonate a phenol, to do a proton transfer, than it is to do an SN2 reaction with any potential benzyl bromide around. So in this particular case, it's not going to be a significant side reaction, but had you added a lot of excess alcohol, it potentially could be a side reaction, because the Williamson ether reaction itself is a slow reaction. So if it's slow, that means that the benzyl bromide won't be immediately consumed in the reaction. It will be present, and if you have excess hydroxide, it would also be present. And we know these two can react together in an SN2 reaction. If this was a major problem, major side reaction occurring, what could we do, right? One thing we could do is basically change the base, right? Because one of the things that we know about hydroxide is that while it's a fairly strong base, it's also a strong nucleophile. We want it in this reaction to act as a base, not as a nucleophile. So what can we do? We can use a different base that's essentially non-nucleophilic. So for example, sodium hydride. We already talked about the fact that hydride is a non-nucleophilic base. It is not polarizable enough, because it's a very small atom, to act as a good nucleophile in a nucleophilic substitution reaction. Another good non-nucleophilic base is something like potassium tert-butoxide. That contains a bulky tert-butyl group, which prevents the nucleophile from being able to do backside attack in an SN2 reaction. So if we had used one of these non-nucleophilic bases, the side reaction of the base acting as a nucleophile would be shut down. However, we're not doing that for multiple reasons. The first reason is we're not going to use an excess of hydroxide, and therefore there should be no more hydroxide around because we know it will completely react with the phenol in the acid-base reaction. We're taking advantage of the fact that phenol is more acidic, and so we will get complete deprotonation to form phenoxide, which will be much faster than any potential side SN2 reaction. The other reason we're not using the non-nucleophilic bases are they're just more expensive, more hazardous, or just not as convenient to use as hydroxide. The reaction, if you were doing it in the lab, would be monitored. The progress of the reaction would be monitored by TLC. TLC, again, stands for thin layer chromatography. So to do that, you take a piece of plastic backing, which is coated with silica gel, create a starting line and some initial marks where you're going to spot some solutions. On the left here, you would spot the reference spot of the unknown, in this case, phenol. And then on the right, we would spot the reaction mixture, and we can do that progressively as time goes on and the reaction continues. So this is one potential TLC plate that you might be able to see. And in this particular TLC plate, we see in the reaction mixture lane on the right, there is some unreacted phenol. That tells us that the reaction has not gone to completion because some phenol remains in solution. So what we could do is continue the reaction, continue heating the reaction under reflux, or we could proceed with the reaction and isolate what product we have, realizing that we're not going to get 100% yield of the product because of the incomplete reaction. Notice how the ether product moves up higher on the TLC plate. That's because ethers are not as polar as alcohols or phenols. Remember that the OH group can participate in hydrogen bonding, so it's going to form a stronger interaction with the polar silica gel on the backing of the TLC plate than an ether would. So they form a stronger attraction, and the alcohol or phenol doesn't move as far as an ether, which forms a weaker interaction with the silica gel. So one thing you're going to note when you look at the activity is that this particular reaction has to be heated under reflux. Which reactions have to be heated under reflux? Well, they are the reactions that take a long time to complete. In order to speed up the reaction, what we can do is give the reactants more energy by applying heat to the reaction, right? That gives more molecules enough energy to overcome the activation energy barrier of the rate determining step. So many reactions, particularly organic reactions, need to be heated. The problem with heating a reaction is that reactions are typically done in a volatile organic solvent. So if the organic solvent is volatile, when you heat it, it will evaporate. So that would mean that in order to maintain a solution, we would have to continually be adding more and more of the solvent because the solvent is evaporating under the heat. In order to prevent the solvent from evaporating, what we can do is utilize a condenser. A condenser is the piece of glassware that you see here that's on top of the round bottom flask. It has what we would call an inner and outer jacket. On the inner jacket, that's where the vapors will come in contact with, and the outer jacket is where you would apply water from a hose. So for example, what we would do is we would attach a hose from a water source into the bottom. You can see the arrow going in on the bottom here. And then water, the pressure will fill up the entire outside jacket until the water goes out on the top. If you were to apply the water from the top, then it would fall down, not create as much pressure, and it would not completely fill the outer jacket, and thus we would get less efficient cooling. So the water goes in on the bottom for the most efficient cooling process. Okay, so what else do we see here? On the bottom of the round bottom flask, this is called a heating mantle, right? It's controlled by a variac or some other controller, which is supplying heat to the reaction mixture. As the solvent is evaporating, it boils, right? So we get bubbles forming. And then those vapors fill the inner jacket of the condenser and gets cooled by the water that's flowing through. And then they will condense back into a liquid, the solvent liquid, and which will then move down by gravity and drip back into the reaction mixture. You can see on the diagram, it mentions what's called a reflux ring. That's basically the point at which you can see, the top point at which you can see condensation of the solvent vapor. So we would ideally like this reflux ring to be around 1/3 to 1/2 of the way up the condenser. If it gets too far up, you have the potential to lose some of your solvent through the top of the condenser through evaporation, which we would like to avoid. Notice that there's no stopper or anything at the top of the condenser. This particular reaction is okay to have it completely open to the atmosphere because it's not water or air sensitive. We would not want to put a stopper in there because we never heat a closed setup, right? If we were to heat glassware that is completely sealed, you could potentially have an explosion. So what would happen if you, once you reach boiling, right, and you see drops forming on the condenser and they're falling back into solution, what happens if you continue to heat the heating mantle and increase the amount of heat supplied to the reaction? You might think that the temperature of the reaction would go up, but it actually doesn't. It would remain constant, and it would remain constant at the boiling point of the solvent. So if you heat if you turn up the heating mantle, what actually happens is you speed up the rate of evaporation. You're going to get more bubbles, right? You'll see more dripping happening at the condenser, and eventually the reflux ring will go up, but you actually will not be increasing the temperature of the reaction until you potentially were to evaporate all of the solvent off. Then eventually the reaction temperature would go up, but not until that time. Okay, at the end of the reaction, we need to purify the product, particularly because it's common for this reaction not to go to completion. So you're going to have a mixture of unreacted phenol, your ether product, and any potential side product, and maybe even some unreacted benzyl bromide as well. So we need some sort of purification method. The purification method that is used is recrystallization. Because it's a solid product, we can utilize a recrystallization for purification. And one of the things that's noted about the ether product is that it tends to be very soluble in hot ethanol, but insoluble in water. We can take advantage of the fact that water and ethanol are miscible solvents and do what's called a mixed solvent or a two-solvent recrystallization system. So instead of just using water or ethanol, which we actually can't do, it's too soluble in ethanol for recrystallization and not soluble in boiling water. So we're not able to just use water for the recrystallization, but we can utilize the mixed solvent to recrystallize. And this is how it works. And dissolve it in a minimum amount of hot ethanol. Remember, it's more soluble in ethanol. And then we can dropwise add in the second solvent that it's not soluble in, which is water. And because ethanol and water are miscible, it's still going to be one solvent. So you're not going to get two layers like you would with an extraction process. So as the water and ethanol mix, you're changing the amount or the percentage of ethanol and water in the mixture as you continually add more water. Eventually, the water outcompetes the crystals for solubility in the ethanol, and the water essentially displaces the solid so that it will not be as soluble anymore in the ethanol. Once you reach a cloudy state, right, it's essentially going to be close to what's called supersaturation, where nucleation and crystal growth can occur. So at that point, you would put it into an ice water bath to allow it to cool, and hopefully crystals will grow. Okay, that's it for the pre-lab lecture. What you want to do is get into your groups and complete the activity.